We have a large room and a small group. Feel free to move forward. So welcome. We're here today to talk about introducing the OpenDataPlane SIG. And what I really like to do is talk about sort of a whole recap of what ODP has been all about, where we've come from, where we're going, and some Q&A. So since this is a fairly small group, feel free to ask questions at any time. So the main motivation behind OpenDataPlane is to satisfy the diverse needs of two separate communities. Okay, community one is the community of application developers, and community two is the platform vendors. And while these two obviously work together, they also have very competing needs and interests. An application developer's primary interest is in deploying their application as widely and as easily as possible. And to do that, they would like to be able to write their application once and be able to have it not just run anywhere, but be able to accelerate anywhere. They'd like to be able to take full advantage of whatever hardware acceleration is available on any given platform without any great effort. And that would allow them to focus on the application rather than the platform, because the platform for the application developer is simply a means for delivering that application. Platform vendors, by contrast, have a very different motivation. They're trying to sell platforms in the marketplace. And in order to do that, they want to be able to support applications, obviously, but also they'd like to be able to demonstrate their added value by allowing these applications to fully exploit their intellectual property without requiring application changes. A sure way to kill any sale is, I've got this great platform. Now, if you just rewrite your application, then this is the benefits you'll get. That doesn't get very far when talking to application writers and customers. So ODP is really trying to strike a balance between these two diverse communities. If we look at the history, we actually started in 2013 with the founding of what was then the Linaro networking group. So ODP was the foundation project for that group. We then went through a number of releases, pre-releases, releases, and as of this year, we have our second long-term stable release, which we've codenamed ODP Tiger Moth. We also transitioned from a group to a SIG structure, and we're celebrating the ODP's 5th anniversary at this Connect, since it was 5 years ago at the Santa Clara Connect that the project was first announced. So at lunch today, feel free to have a slice of cake and, and think of the anniversary. ODP's been actually deployed in many different application areas. So in things like telecommunications, for evolved packet core networks, base stations, pico to macro, base station backhaul with dealing with fat encrypted pipes, other environments in that area. Enterprise and cloud is another with various firewall applications. Security and VPN gateways, et cetera. And increasingly, because ODP can be deployed in things that don't look like traditional servers, it's also been deployed in SmartNICs and edge devices. The platforms of interest that ODP is really focused on are two. One is what I call general server platforms. These tend to be software-centric, in which cores touch every packet. They tend to have standardized acceleration, which means we either have special CPU instructions, so for instance an AES instruction to accelerate that operation, or they have plug-in cards with associated PCIe latencies, where I have an attached accelerator. They come in standard form factors, which is mainly rack chassis, and their leading architectures tend to be x86 and AR64. These are deployed mainly in cloud-type environments, and it's an important class of platform. And obviously, other products like DPDK clearly come from this heritage as their main focus. The other type of platform that ODP is specifically interested in is what we'd call network SoC-based platforms. And these tend to be more hardware-centric in that packets may bypass cores either partially or completely. They tend to have innovative and non-standard approaches to acceleration, and this actually constitutes the value-added IP that vendor is providing. Okay, and the challenge is to allow applications to exploit that IP without requiring application changes. They tend to have varying I/O, for instance, integrated I/O that doesn't involve PCI adapters. They have varying form factors, so they could be packaged as a smart NIC or other embedded device. And the interesting thing about these platforms is their leading architectures tend to be ARM as well as custom. Okay, there's various proprietary architectures that go into this, and being essentially architecture agnostic, ODP supports them all. So these are mainly for edge and embedded environments. So one of the ways we've characterized this difference is to talk about software implemented versus software defined networking. So in a software implemented data plane, such as provided by DPDK, NetMap, or Packet Direct, if we look at, say, for instance, an IPsec application that's doing a lot of heavy lifting, the application has to adapt to the various types of accelerators. Okay, there may be none, in which case things have to be done in software. There may be a crypto offload engine or an IPsec crypto device, different types of approaches to this, which is really has to all be done in software and largely in, with application awareness. In software-defined approach, instead, the application is really focused with configuring and overseeing a packet flow pipeline, if you will, from input to output. And whether or not packets have to go through the particular cores or application logic is really a function of how that's configured. So for instance, in a IPC look-aside mode, packets may go to that core, but in an inline mode, they may be automatically decrypted on receive and re-encrypted on exit without specific application involvement. So what this is really doing is illustrating ODP's role as what we call an innovation boundary. For applications, this means that functions, they can define functional needs without concern for how they're met. And application writers are not really required to be platform architecture or hardware internal experts in order to be able to get the best value out of a particular platform that they happen to be running on. So this permits portability across all conforming implementations with at most a recompile. And that's really the main goal here. Moreover, we define an ABI, or an application binary interface, that permits application binary portability within an instruction set architecture. So if I have different platforms based on AR64, a single binary can run compatibly across all of them and yet exploit the unique acceleration capabilities transparently that each of those platforms offers. So this really avoids vendor lock-in without the downside of least common denominator limited functionality, which is often the case when I'm adopting a one-size-fits-all type approach to acceleration. By contrast, for SoC vendors, the advantages are that the implementation internals are not exposed across an API boundary. In many cases, if you have a set of APIs that basically define how functions are implemented, it really constrains the platform vendor as to how they can do it. It's like, well, I really have no choice. The API specifies I must do it this way, even though I know I could do it much faster and provide the same function to the application without this constraint. So this allows APIs to be realized in hardware, software, or any combination without impacting applications, which is really an important point. Because vendors are not constrained by a fixed software-centric implementation model, this permits their unique platform value to be exposed without requiring application changes, which is really the killer of dilemma that any IP innovator has. It's that, hey, I know a new way of doing something that is 10 times faster, but I can't deploy it because it requires all these application software to be rewritten. More importantly, from an internal standpoint, I mean, every new platform typically has an associated SDK. And if I have multiple generations of products with multiple SDKs, these tend to be a huge support burden internal to the company. And ODP essentially can serve the role as a universal SDK, which avoids internal fragmentation, which is another important benefit for SoC vendors. So the way that ODP is achieving this is by intentionally using abstract APIs. So the APIs allow the application to focus on the what, while the implementation focuses on the how. So applications deal with functional needs, not implementation details. For instance, packet operations are performed on ODP packet T objects. And what is an ODP packet T? The answer is the application doesn't know or care. That's an implementation decision as to how that concept is realized. So if we look at this illustration, this is just showing sort of a brief overview of some of the APIs that ODP provides for packet manipulation, where an ODP packet T object is passed as an argument to these APIs to address packets, to manipulate them, to provide various transforms on them, and ultimately to send them on their way. And all this is all done without the application being explicitly aware of how these transformations are occurring. So again, the SAW implementations, not being constrained by this, can easily support hardware, packet and buffer managers, queues, schedulers, et cetera. And this is really the key to providing differentiated value without requiring application changes, which of course is exactly the domain in which Linaro has always operated, is that by providing an open source implementations for non-differentiating value, it gives the application writer and the SoC vendor the freedom to really focus on their differentiating value, which is really what makes them stand out from everyone else. So if we look at the structure and scope of ODP, there are really a number of different components that are associated with this. The objects in green here are really the work product of the ODP project itself. So this includes the API specification, which is the innovation boundary, and reference implementations, which are pure software reference implementations of ODP that are used to serve two purposes. One is they give a concrete example of how these APIs can be implemented. And secondly, they provide a platform-neutral starting point for anyone who wants to do a customized, accelerated implementation of these APIs. So typically, since these are written just to run on Linux, if you have a Linux kernel on your SoC, you can be up in an afternoon with this running on your thing, even if it's a completely different architecture or has something very different. And then going from there, you'll replace various pieces with customize things which accelerate. So maybe, for instance, you have a hardware buffer manager. Okay, so rather than using the software buffer manager that is included in the reference implementation, you'll replace that with your hardware buffer manager, et cetera. So we actually have two implementations that we do this. One is a pure software implementation that runs Linux, and the other is what we call an ODP faceplate on top of DPDK. Many platforms are software-centric and already have a DPDK implementation running on them. If you have a DPDK implementation running on them, this reference implementation essentially just maps the ODP API directly onto the DPDK APIs so that applications written to the ODP APIs can run and get the same benefits as if they had been written as native DPDK applications. The blue items here are, the sort of the secret sauce that platform vendors provide, which is native implementations of ODP that offer that real acceleration capability. And then the final green piece on top is the validation test suite. So it's great to have all these different implementations of the API, but the question is, how do you know that they all are correctly implementing it? Well, we provide a open source reference validation suite, which can be used by both vendors and implementation writers, as well as application developers, to verify that implementation X actually conforms to the API. So the way this works in practice from a cross-platform support is shown here. If I have an ODP application written to the API, then if I'm running, for instance, on a software-centric ARM or x86-based platform that has DPDK, it will use the ODP faceplate to map the ODP APIs onto DPDK and get good performance, okay, on that platform at basically no cost to the application developer or the platform provider. If, on the other hand, the platform has a native ODP implementation that's going to exploit whatever unique IP is available on that platform, and these are typically ARM-based SoCs, then the same application, possibly even the same binary application if you're talking about AR64 across the board, will get optimal performance because it's transparently accessing those native acceleration features. So the question is, how to structure this. What Linaro did was they transitioned ODP into a SIG, a special interest group, basically to recognize the project maturity, provide autonomy, and provide more flexible membership options, reduced cost, resource commitments, ideally for smaller companies, universities, et cetera. And the goal was to enable more responsive and focused attention to member and community needs. This is all in support of the workflow that we've been adopting for the past several years, which is an iteration between architecture, API definitions that support that, and implementations that realize those across multiple platforms, all in a positive feedback loop to result in APIs that are both portable and efficiently implementable across multiple platforms. Where we're going, right now we've been looking at several new areas of APIs, adding support for compression, for additional crypto algorithms that are particularly suitable for 3GPP, mobile communications, the Snow and Kasumi algorithms. Some lightweight flows, which is an enhancement to the ODP scheduling model, and we'll actually be covering that later this afternoon, 12:30, right here in session YVR18-201. So I invite you to come back to learn more about that. And tunneling. One of the issues that you have increasingly is applications, packets are tunneled in other protocols, and so providing generic decapsulation and encapsulation protocols is something of interest. One of the other things we've really been focusing on this year has been improving the scalability and performance. So we've now, thanks to the availability of platforms like ThunderX2, we've been able to do testing on large core count systems, greater than 200 cores, and continued streamlining of the software scheduler that ODP includes, which is now showing performance within 10% of poll mode operation, which basically is a good way of providing proof of the scalable model. The other thing we're doing, which is joint with the new Linaro networking and telecom SIG, is looking at additional bug fixes and enhancements for tuning and performance scaling on ARM-based platforms, since that group is chartered with working directly with the DPDK upstream. And we're working with DPDK for this faceplate, we've discovered that there are a number of limitations in DPDK today which really prevent it from scaling as efficiently as we'd like. And there's also been some interest expressed in more high efficiency east-west message passing for virtualized and containerized applications. So that's another area which of interest. So, any questions? Yes. So the question was, who are the vendors currently using ODP? We've, I mean, I think the announced ones are Cavium, Marvell, and we know there are a number of others. I don't know how well they want to publicize themselves. Any other questions? I'm sorry, could we get a microphone? Unfortunately, it's a very large room.
I was just wondering about the status and whether it's in these vendors, or how close are we to shipping products and being kind of real-world products?
Real world products have been shipped. Yeah. So the question was you know, how many real world products have been shipped with this? And the answer is there have been real world products shipped. Unfortunately, a lot of the vendors who've done so have not chosen to publicize that. So this is really viewed as plumbing. You know, I mean, when I'm selling a vehicle, you know, most people don't advertise, and it has an engine, you know, or it has a steering wheel. So that's one of the problems with working in deep infrastructure, is that it's plumbing, it's useful, but it tends not to get the headlines. Anything else? Yes.
What do you think? What would be the most important thing to
I'm sorry. I think we got a mic coming here.
Sorry. So question is, what do you think about what would be the most important thing right now for the ODP to be more broad used, more, you know, publicly recognized, and chosen as the main development platform by the developers?
That's a good question. I think the answer would be probably if there were more high-profile applications that basically came out and said, "Hey, and we're doing all this with ODP," but that's unfortunately not under our control. So we've tended to it's tended to be more word of mouth in that regard. Any final questions? We have a few seconds. Okay, well, thank you very much.